Hello everybody, this is Dr. Christopher White and welcome back for part 2 of Deformation 2. Okay, so initially we were talking about strike-slip faults. If you remember, a strike-slip fault is where the pieces of rock either side of the fault are moving laterally relative to each other, but there's no change in height relative to each other. So the next type of faults are the dip-slip faults. Now in this case you are going to see the blocks changing height relative to one another. So dip-slip faults consist of two parts. We have the footwall and the hanging wall block. So the footwall block is essentially the part of the dip-slip fault that does not move. It stays still. The hanging wall block is the block that actually is in motion. It will go up and down relative to the footwall block, depending on the conditions. The term footwall block and hanging wall block are old mining terms. Obviously the footwall block is the block you walk on and the hanging wall block is the block above your head. So if we look at this picture here, this is kind of the old-fashioned view. So as we can see, here's one block. Our fault plane is quite clearly there, coming through here, and this is the other block. We can see that as this is the block you're standing on, footwall block, this is the block above your head, hanging wall block. Now obviously in the more modern definition, this is the hanging wall block because it's the block that's actually doing the moving. So when it comes to these dip-slip faults, let's talk about the first type, which is a normal fault. And so you can see here, this is a normal fault. So you can see in the case of a normal fault, the hanging wall block is dropping down relative to the footwall block. Now, as we can see from the arrows, this normal fault is associated with a tensional regime. So the rock is being extended. Okay, so normal fault equals extension. The crust is being stretched essentially. So think situations like divergent plate boundaries. So what's going on? Now remember, we're dealing with a situation now where the rock cannot stretch. It must behave like a solid. So we can't stretch our rock and make the layer thinner to make it become longer. Okay, so how do we accommodate the fact that the geologic forces are trying to pull this piece of rock and make it longer, but the rock can't do that easily because it has to behave like a solid. So how does it do it? Well, it does it first of all by fracturing, and then it does it by allowing pieces of rock to move relative to each other. So if we were to imagine that we took this block here and we put it back to its original starting position. Okay, so imagine the distance from this point here to this point here. Okay, so it would be probably there to probably somewhere about here, give or take a little bit. Okay, now what happens? Well, as we let this block drop, you will notice that as it drops down the fault plane, the distance from this side of the footwall block to this point right here gets larger, doesn't it? So the distance from here to here increases the further down this block goes. And so what we have is we have a method of making the block go from this long to this long simply by allowing this piece of rock to drop down. And at all times these pieces of rock are behaving like solids. They're behaving in a brittle fashion. Okay, so that's a normal fault. So what about a reverse fault? Well, you can see straight away for a reverse fault, the hanging wall block is coming up relative to the footwall block. You will also notice the arrows are indicating that we have a compressional regime. So the block of rock is being compressed. So this is most likely to be associated with environments like convergent plate boundaries, where we have pieces of rock coming together. So what's happening? Well, you can see, as I said, this block's coming up relative to this block. So this is the hanging wall. This is our footwall. Now, once again, if you imagine that this block is in its starting position, we're going to imagine a distance from this point here to this point here. Okay, so if we imagine that the distance from here to this point would probably be somewhere about here, wouldn't it? Where the tip of the arrow is, tip of the pointer is. Now, by forcing this block upwards, we make the distance from here to here smaller. So as this block gets higher and higher relative to this block, the distance from there to there gets smaller. And so once again, what are we doing? Well, in this case, we are accommodating the fact that the rock is being squished. We are accommodating the fact the rock is being compressed and wants to get shorter. We're making that happen by letting the blocks of rock move relative to each other. And so we start off with a piece of rock that's this big, and we'll end up with a piece of rock that's that big. So we're making the length of the block smaller by allowing this block to go up relative to this block. Now this is the situation we have for both reverse and thrust faults. So these two types of fault behave in the same way, but there are very, very slight differences between them based on which we use to separate the two different types. So we'll obviously talk about those. Okay, so you have to remember these dip-slip faults are a method of accommodating compression or extension, okay, by allowing pieces of rock to move relative to each other, because the rocks have to behave in a brittle fashion, because they cannot be stretched, they cannot flow, they cannot behave in a ductile way. Okay, so this diagram here, once again, exactly the same situation. This is just demonstrating the footwall block is the block that's stationary, and in an old mining term, it would be the block that you walk on. Whereas the hanging wall block is the block that does the moving, and in terms of mining, it would be the block above your head. Okay, but that's not really that important. This diagram was just in there again just to drive that point home. All right, so normal faults. Normal faults are produced in tensional regimes, so where we have extension of the crust. In the case of a normal fault, the hanging wall drops down relative to the footwall. And so one side of the fault slides down relative to the other, just said that, so ignore that. Now, by allowing the hanging wall block to drop down relative to the footwall block, what do? Well, we simply increase the distance from this side of the fault to this side of the fault by allowing this to happen. So, as you can see, if we allow this to happen, to go far enough, you can see we actually create a gap between this point and this point. So this essentially is what's referred to as the gap, and that essentially is just a measure of how far the hanging wall block has moved. So once again, we've seen this diagram already, but this is the diagram that it shows you essentially what's going on. We have two normal faults in this case. We have a normal fault right here, and we have a normal fault right here. And so as you can see, as we move this block that way, this block that way, this block drops down to accommodate the movement. And so by doing so, we take what was a 50 centimeter block and we extend it to make a 60 centimeter block. Relatively simple. So here we go. So here's a nice example of a normal fault. Remember, we can work out which way the rocks are moving by simply looking at the marker beds, the indicator beds. So we can see that we have these two very, very distinct darker layers here and here. And we can see here they are again, there's one layer there, and there's another layer there. And so we can see that this layer here corresponds to this layer here, and this layer down here corresponds to these layers here. And so clearly what's happened is this side of the fault has dropped down relative to this side of the fault. So this is our hanging wall, this is our footwall, and we can see the fault plane itself is coming up here like so. You can just you can literally see the fracture in the rock face. So it's a nice easy fault to spot. Okay, now that was relatively simple. Now this is an environment where we actually have lots and lots of normal faults. So if you've ever flown over an area like Utah, you will have seen terrain that looks like this. Okay, now this terrain is sometimes described as a basin and range province, or it's sometimes referred to as Horst and Graben province. So what's going on? As you can see, what we have here is we have high ground, valley, high ground, valley, high ground, valley, high ground, valley, etc., etc. You can see we have these constantly repeating ridges, can't we? Now, in terms of what we refer to these in geology, well, we refer to these as Horsts and these valleys as Grabens. So the Horst is the high ground, and the Graben is the piece of rock that's dropped down, creating a valley. Okay, so the Horst is the high ground, the Graben is the piece of rock that drops down, making the valley. So this is an example of a terrain produced by extension. the rock's being stretched. So how does this actually work? Well, in this instance, we have a couple of ways we can achieve this. So if we look here, this is kind of the classic version of a Horst and Graben structure. Okay, so we have one block of rock here, one block of rock here, we have a normal fault here, a normal fault here, and so because we have these two normal faults here and here, it allows this block to drop down relative to these two blocks either side, just like the diagram we saw 2 slides ago. So essentially it's just like this. These would be our Horsts, and this block here would form the Graben, the valley. So high ground, valley. Now that's the simplified version of how we end up with these Horsts and Grabens. Most of this basin and range province, on the other hand, is actually produced by a type of fault which we call Allosteric fault. So in the case of Allosteric fault, the fault, so the fracture, isn't a nice continuous straight line. It actually curves. Now what does that mean? Well, if we look down here and we look at these blocks here, what's happening? Well, here's a fault block. You can see it there. Okay? So this fault block is dropping down, but because the fault plane itself is curved, it doesn't drop straight down. Instead, it pivots. So this part of the fault block essentially stays where it is. So this part of the fault block doesn't move. The rear part of the fault block pivots and drops down, doesn't it? So what this means is as this block drops downwards, this part of the block stays exactly where it is, creating the ridge, whereas this part of the block drops down, creating the valley. Now this is referred to as a half Graben, because you only have one fault, but you still produce the same structure. So a normal Horst and Graben structure, you have 2 faults. So this would be a normal Horst and Graben structure. Okay, you have a normal fault here and a normal fault here. In the case of Horst and Grabens created by just one Allosteric fault, it's referred to as a half Graben. But you can see how it works by making this part of the fault block stay where it is and making this part of the fault block drop down. Essentially you create a ridge of high ground here and a depression here. So we have our Horst here and our Graben here. And so this is the result of a Allosteric fault, which, as I say, is the result of a curved normal fault. So it's a special type of normal fault. But once again, this basin and range province is the result of extension. The crust is being stretched. Okay, so that's basin and range province. So what about reverse faults? Well, reverse faults are caused by compression, as we discussed. In the case of a reverse fault, the hanging wall will move up relative to the footwall. Now, reverse faults essentially can also be called thrust faults. So what's the difference between a reverse fault and a thrust fault? Well, it's all to do with the angle of the fault plane here. Okay, the classic definition is if the angle of the fault plane is 45 degrees or less, it is considered to be a thrust fault. If the angle of the fault plane is greater than 45 degrees, it's considered to be a reverse fault. So that's the difference between the two. Reverse faults tend to have quite steep fault planes. Thrust faults tend to have quite gentle fault planes. And you'll see some diagrams in a second to demonstrate that. So obviously what happens? Well, obviously as we push the hanging wall block over the top of the footwall block, we produce what's referred to as an overlap. Remember, with a normal fault, we produced a gap. With a thrust fault or reverse fault, we produce an overlap. So we're pushing layers of rock over the top of each other, so they're beginning to overlap on one another. So here's our situation again. So this is our situation we have with reverse faults. So here are our 2 blocks. As we push these 2 blocks, the block here and block here, towards each other, this block in the middle is forced upwards. So this block moves up relative to this block and this block. So we have a reverse fault here and a reverse fault here. Okay. Once again, by doing this, what have we done? Well, we've taken a block of rock that was originally 50 centimeters in length, And by doing this, we've taken that block and we've turned it into a block which is now 40 centimeters in length. So we've accommodated the compression essentially by allowing the rock to behave in a brittle fashion, just as we want it to. So these two diagrams demonstrate the difference between the two different types of faults. So here's a reverse fault. You can see a nice steep fault plane right there. Okay, typically, well, in order to be a reverse fault, the definition is that that fault plane has to be 45 degrees or greater than 45 degrees. Okay. Thrust faults, as you can see, the angle of the fault plane is a lot shallower, and thrust faults must have a fault plane angle, or fault plane dip, should I say, of less than 45 degrees. Most of the time, the fault plane will actually have a dip of less than 30 degrees, so it's really rather shallow. So sometimes these reverse faults can actually be reactivated normal faults. So normal faults tend to have quite steep fault planes. So normal faults, the fault plane can be, normally it will form somewhere in the kind of 60 to 80 degree range. So it'll be, to apologize for that, it will be quite steep. Okay. Now, the thing about geology is that conditions that exist for a period of time in one area will eventually change. So you can have an area of the crust which is under extension for a very, very long period of time, so it's being stretched. And so you end up forming lots and lots of normal faults. Now, a few million years later, that area that was under extension can suddenly find itself under compression. Now, what's going to happen? You have an option. You can either, as your rock's being compressed, make completely new faults to accommodate that compressive force, or you can simply use the old normal faults which are already there. And so a lot of the time what will happen is you will simply end up reusing the old normal faults. And so you'll turn what was a normal fault into a reverse fault. It's just the easiest, the most energy efficient method of essentially accommodating the new compressive force. But reverse faults can also form naturally on their own without the need to reactivate a normal fault. So reverse faults can just form, or sometimes they can also be reactivated normal faults. Thrust faults, on the other hand, they are much lower angle, and typically they are completely new faults. Now, thrust faults are very, very important because thrust faults are the main type of fault when it comes to moving large quantities of rock over substantial distances. So if you want to move a really, really big piece of rock, a reverse fault is actually quite energy inefficient. Because think about it, if you want to make this block of rock go a long way, you have to push it vertically a long way, don't you? So that's going to take a lot of energy, and so that doesn't really work. In contrast, if you want to push this block here a long way, well, that's a lot easier to do because the angle of the fault plane is a lot shallower. It means that you can push this block over very, very large distances with greater ease. It's more energy efficient. So what we're going to see later on when we start talking about things like mountain ranges is you're going to see that thrust faults are actually very, very important when it comes to building up layers of rock and moving rock over quite large distances. Okay, so I'm afraid the quality of these pictures is pretty terrible, but we've got to go over what we've got. So here we go. So here we have a wonderful example of a nice reverse fault. Well, how do I know it's a reverse fault? Well, first of all, we need to find our marker bed, don't we? And we can find it quite easily. We have a big, chunky bed right there, and there's the same bed right here. Now we can see this block here has clearly gone up relative to this block here, hasn't it? So we know this is the hanging wall block going up relative to the footwall block here. And we can actually see the fault plane itself quite easily there. It's picked out by all this broken up material, so it's not difficult to spot at all. So what have we got? Well, there's our fault plane, and we can see the sense of movement there. We can see it because of the marker bed here, and it's a reverse fault now, and that's going to be our overlap. Okay. Now remember, the angle of the fault plane is rather steep, so it has to be a reverse fault. Okay, let's look at this fault here. Right, let's try and figure out what's going on. Okay, well, we need to try and see what's happening, so let's try and find our marker horizon. Well, our marker horizons are quite straightforward. We have this orange layer here, and then we have a red layer here. where you can just make out an orange layer here. There's the same red layer here. And so what you can see is this part of the fault has clearly been forced upwards relative to this part of the fault. Therefore, this must be the hanging wall. This must be the footwall. Okay. Now, as soon as we can see the fault plane itself, it's not difficult to miss. It's coming through right there. I'm sure you spotted it straight away. Okay. Well, as you can see, it's clearly quite a steep fault plane, isn't it? So this, once again, has to be a reverse fault. So there's our fault plane, and there's our marker bed, red bed here, and the same red bed down there. And that's our overlap. And you can see in this case, the overlap is quite substantial. Okay. Now this picture is absolutely horrendous, but it's the best one I could find. So let's see what we can see here. Well, alright, the marker horizon, the marker bed we're looking for, is very easy to see, isn't it? It's right here. It's this black layer coming through here, and there it is again there. Now we can see that we have a situation, don't we? Okay, we can see that if you think about it, if that's our fault plane coming through here, okay, we can see that this block has actually been pushed over the top of this block. Now, I've actually spotted that this is actually incorrect. So if I just go back for a second, okay, the fault plane itself is actually coming down through here, down through there, and the fault plane is actually coming through there like that. Follow the point. So we're starting up here, the fault plane is coming down like this, so it's not a completely straight fault plane. It's got a bit of a curve to it. Okay, so this initial red line is actually incorrect, so please ignore that. That's a complete mistake on my part. Okay, but once we know where our fault plane is, what it shows us, we have a block of rock here, and we have a block of rock down here. And when you start thinking about the logistics of how these blocks of rock must have moved relative to each other, well, the fact that this part of the black layer is overriding and going over the top of this part of this black layer here, which is the same one, means that this block must be being pushed over the top. So this must be a hanging wall block, and it must be going over the top of this block here. Therefore, it must be some kind of either thrust or reverse fault. Now the thing is once again, as we start looking at the fault plane itself, starting up here, coming down here, like so, I think we can agree that this fault plane is not very steep at all. It's quite shallow. So this is going to be an example of a thrust fault, because we can see the fault plane is quite shallow. So now ignore that. That's terribly drawn. Now the sense of movement is correct, but the fault plane I marked out here in red is completely incorrect. So please ignore my epic stupidity. Now this is a thrust fault though. You can see the sense of movement, and you can see how the fault plane is very low angle. Okay, so this diagram here summarizes the 4 different types of faults. So we have normal faults, reverse faults, and thrust faults. Now these are dip-slip faults, and then we have strike-slip faults here. So remember, normal faults, reverse faults, thrust faults, the blocks of rock will move, it will change height relative to each other. The footwall block stays still. The hanging wall block goes up or down. In the case of strike-slip faults, the blocks move laterally relative to each other, but they do not change height relative to one another. And this diagram here summarizes the same thing. I'm not really going to go into it too much, but you can see here we have normal faults over here. So we have one block dropping down relative to another block. We have a reverse fault here. This block is coming up relative to this block. And we have a strike-slip fault here where these 2 blocks are moving relative to each other. There's no thrust fault on this diagram, but it does kind of give you an idea of what's happening. And it does also kind of show you how sometimes what is the hanging wall block for one fault can also be the footwall block for another fault. So if you have a system where you have multiple fault planes all moving at the same time, you know, it gets quite complicated. Okay, so what we're going to do is we are going to stop here. And do you know what? Before we go any further, let's do the code word quiz. Let's do the code word for this particular lecture. So if you remember, the code word for lecture 1 was a piece of fruit. So naturally I asked my children for the name of another piece of fruit, and the answer that I got first was, of course, gummy bears. So the code word for this particular quiz is gummy bears. All right, everybody. So once again, get up, have a walk around, glass of water, cup of tea, coffee, whatever you fancy, and then come back for part 3 once you've had a bit of a rest.